Ever wondered how those massive hunks of metal stay up in the air? It's not magic, folks, it's science. And today, we're diving headfirst into the captivating world of aerodynamics to understand how two-engine planes, those marvels of engineering, conquer gravity and soar across the sky. We're talking about the fundamental forces at play: lift, thrust, drag, and weight, and how they work in perfect harmony to keep these planes aloft. From the shape of the wings to the power of the engines, we'll break down every aspect of this aeronautical ballet. So buckle up, get ready for takeoff, and prepare to have your mind blown wide open. Let's talk about lift, the force that makes flight possible. Think about a bird's wing or an airplane's wing. It's a shape called an airfoil. This design manipulates airflow. Air flows over and under the wings. The curved surface speeds up the air above. Faster air creates lower pressure above the wing. Higher pressure below generates lift. This lifts the plane skyward. Birds, bats, and insects use the same principle. We've learned from nature to conquer the skies. Now, lift is crucial, but it needs a trusty sidekick: thrust. That's where our two engines come in, those powerful beasts roaring with purpose. Whether they're jet engines or turboprops, their mission is the same: generate thrust. They do this by sucking in massive amounts of air, and either combining it with fuel for combustion in a jet engine or spinning propellers in a turboprop. This process creates a high-pressure exhaust that's expelled out the back, propelling the plane forward. This forward motion, this relentless push, is what creates the airflow over the wings that we talked about earlier. Without thrust, there's no airspeed, and without airspeed, there's no lift. Think of it like this: the engines provide the oomph, the driving force, while the wings, with their clever design, harness that force to generate lift and keep us soaring. Chapter 3. Now, our plane is happily generating lift and thrust, but it's not all smooth sailing. It faces two formidable opponents: drag and weight. Drag is like the air resisting the plane's forward motion. It's like trying to run through a swimming pool. Engineers streamline aircraft designs to minimize drag, but even the sleekest plane has to contend with it. And then there's weight, gravity pulling the plane down. Overcoming gravity's grip is crucial. Engines generate thrust to counteract drag and weight. It's a delicate balance, a constant tug-of-war. Chapter 4. Now we've got our plane flying, but we need to steer this bird and keep it stable in the air. That's where the control surfaces come in. The ailerons on the wings, the rudder on the tail, and the elevators on the horizontal stabilizer. These movable surfaces act like the plane's steering wheel, allowing the pilot to control its orientation. The ailerons control roll, the rudder handles yaw, and the elevators manage pitch. But what happens if one engine fails? This is where things get really interesting. Modern twin-engine planes are designed to fly safely on just one engine. The pilot can use the rudder and ailerons to compensate for the asymmetrical thrust, keeping the plane flying straight and level. It's a testament to the ingenuity of aerospace engineers and the skill of pilots that these massive machines can handle such situations with grace and precision. And there you have it, the fascinating principles that keep two-engine planes soaring through the skies. We've delved into the world of lift, thrust, drag, and weight, the fundamental forces that govern flight. We've explored how the ingenious design of airfoils manipulates air pressure to generate lift, how powerful engines provide the necessary thrust to overcome drag and weight, and how control surfaces allow pilots to maneuver these magnificent machines with precision. Remember, modern twin-engine airplanes are designed to fly safely even if one engine fails. Safe travels.